we would again need to look up the Z table. Now this time it is gonna be a different one. We'll look at this one. So 2.32. Okay, so where is 2? 2 is right here. 2.3 is right here. 3, 2 is 1.02 E. So E is the E exponential 002. So this is exponential table 1.02 E 002. So this is what we got. And when we look up 3.49, so 3 is right here, 3.4 is right here, 9 would be exactly at the end. It is 2.42 E exponential 004. This is the one right here. So in a way, 1.0 E exponential 002, it can be written as 1.02 divided by 100. So whatever digits that you have in exponential would become the number of zeros in denominator. You with me?
No.
Okay. E exponential, so 1.02. So let me just go to the Excel. So 1.02 E exponential 002. Okay, this is the value that we have. It can also be written as 1.02 divided by E exponential 002 would be mean 2 zeros in the denominator. If it would have been 1.02 E exponential 003, then it would have been 1.02 E divided by 1000.
Okay.
Whatever the number of digits that we have after exponential become the number of zeros that we will have in the denominator. Okay. So 1.02 divided by 100, which is 0.01 or 1.02%. Right? Now 2.42 E exponential 004. Okay. Now this can be written as, you want to give it a try?
Yeah, it's so it's 10,000, 1,000? No, wait, 4 zeros would be 10,000.
10,000.
Yeah.
Right.
So
Absolutely.
0.00242 or something like that.
Right. Okay. So if I then we need to do the LCM of both these. So you remember LCM?
Yeah.
Oh, you do? Fantastic. I had to, when I went through this, I had to take LCM class. it was that long. So basically, this particular figure, we can also write it. So if we 0.024%, and it will be 1.020%. Right. So what I've done is denominator is 100 here for both the cases. So LCM is gonna be this plus this. This is 1.044. So if we add this 1.02%, 0.024%, we get 1.04%. 1.044%, right? So 1.04% now. %. Okay, let's look at this figure right here. Now, if you want to convert it back into exponential figure, so 1.04% would mean 1.04 divided by 100, right?
Mm-hmm.
So that means 1.04 e exponential 002.
2, yeah.
Right? 1.04 e exponential 002, right?
Mm-hmm. Correct.
This is what we have done here.
Mm-hmm.
Now we need to look up this value in the z table. Now why we are doing that? Because the upper and lower are not the not the equal number of standard deviations. Had it been equal number of standard deviation, we wouldn't have bothered. We know exactly, if it is 3 on both the sides, we know 3 is the sigma value, right? But it is 3.49 one side and 2.32 one side. We want to calculate the correct capability, right? So
Okay.
we need to look at 1.04 e exponential 002. Now the way to look at it here, first we find the portion where it has 002. So 002 is right here.
Mm-hmm.
Then we look up for 1.04. So there it is. 1.04.
There we go.
So this is 2.31.
2.31.
Okay, so if we converted the Z bench or long term, that we get is 2.31 is the sigma value of this particular process. Remember, I told you long term process become much more inefficient. So in short term, you need to add 1.5.
Mm-hmm.
Right? So 1.31, right? Sorry, 2.31 is ZLT, which is long term. So we add 1.5 to it. 3.81 is the Z short term. Okay.
Mm-hmm.
So I know I mean, in one go, it's going to be difficult to understand or absorb everything, but just understand the concept. Rest, I think, you would not need to calculate.
Good. At the formula, I'll be able to muddle through, but wow.
No, but then it's not required. What required is the concept.
Okay.
Right? Why we took the LCM? Because obviously, these two values were different. Right? So on one side it was where it is, yeah. On one side it was more standard deviation. On the other side it was less standard deviation.
Right.
So can we say the process working at 8 sigma level? No, we cannot, because here it is 7 sigma. Can we say the process working at 7 sigma level? No, we cannot, because on the upper side it is 8 sigma, right? So what is the sigma level? So what we did, we took the LCM of both these. So instead of taking LCM of standard deviations, we calculated the Z value. We took LCMs of the Z value, converted it back to these values.
If you just would like averages, it would be easier. To 7.5. Move on.
Yes, but you remember, averages are bad.
I know.
Right. See, I'll tell you what, statistician would never make it that easy. Right. So
exactly. Everybody do it if it was that easy.
Absolutely. Otherwise, everybody would be statistician. So, they make it complicated on purpose. All right, then. So, so we know how to calculate the Z value now. Okay. So there is a soap manufacturer. I will not. Okay. So let me do this, Scott. I will share this exercise with you. Share this exercise with you, and the next one as well, along with the Z table. Would you be able to calculate the Z score?
We're
I
gonna
mean,
find
would you be
out.
able to get time after the training to do some
Yeah.
calculation?
Yeah.
Okay, perfect. So let me send it to you while we are on the call. Okay, just give me a moment. Let me just copy paste. Okay. Now, what happens when you have too many presentations open? You need this. I will send it to you anyways. You need to use the last two Z tables.
Okay. Yeah. Send it over to me.
Okay, it's there. Oh, 626, right. Okay. So I will send it over to you. In the meantime, let's go through some more concepts. There's more of a theory now. So,
Okay.
so there is a concept of process shift. So what we say is typically a process will shift approximately by 1.5 standard deviation in long term. And long-term variation is more than the short-term variation. So, so that's the reason why there's a term called sigma shift. Okay, so what you need to do is always would need to add 1.5 sigma or 1.5 standard deviation to the long-term standard deviation to get short-term sigma level. Okay, BPMO is always calculated on a long-term sigma, long-term standard deviation.
So the long-term sigma,
Yep,
you're adding 1.5
to get to
onto
the
the
short-term.
level, and it's making it better, right? Over long term, it's going to get narrower, correct?
Yes, yes.
Okay. I just want to make sure I was thinking right.
Right. So
Okay.
long term. Let me just understood what you said. Let me just try to understand. So when you say narrower, what do you mean?
The bell curve will get narrower because
In
you're going
long
to
term,
improve.
no. In long term, the process is less efficient as compared to short term.
Okay. Okay.
So
So when you
less
first
efficient.
get the processor better.
Right.
Okay.
So the bell curve in long term would get broader, and in
Okay.
short term it will get narrower.
Okay. Got it.
Okay, perfect.
I was thinking
Now,
opposite, that they would learn. I was thinking they would get better at the process and there'd be less defects. But
right. But then in
they
long
get
term,
more
what they say,
relaxed.
yeah, we get more relaxed. There are redundancies. Some of the processes become inefficient. So that's the reason why, long term is less efficient as compared to short term.
Is there a range? What is short term versus what is long term?
No, they haven't
Talking a
specified the range.
year.
Nope.
It's just
Nope. There is no
long-term,
range
short-term.
as such. Just
Okay.
the term short term and long term.
Okay.
Okay. Now, the process variation, as we talked about, there is a short-term variation, which is generally caused by the common cause variation. And then there are long-term variation, which is common plus the special cause variation, because obviously in long-term, everything will come into play. Okay. There's a table for DPMO to see short-term and long-term. Right. So, and there's another concept. So there is third way of calculating process capability called CP. So all that is not covered. We will quickly go through it. So this is a bell curve that you see. You have a bell curve. You have a lower specification limit. You have an upper specification limit. So the process capability is calculated by the formula called USL minus LSL by 6 standard deviation. So what we are trying to say is, when you difference between this lower upper and lower specification limit, if you try to fit 6 standard deviation here, what is the value that you get? This is what formula is telling us, right? You with me?
Yeah, that's 6 times the standard deviation, right?
6 times the standard deviation, right? Absolutely.
Okay.
And
Yeah, I'm
we
with
know
you.
in a Six Sigma project or in a Six Sigma process, you should be able to fit 6 standard deviation between the mean and the upper and the mean and the lower specification limit, right?
Mhm.
So between the upper and lower
So
specification limit, ideally you should have how many standard deviations?
6 for a 6 sigma.
Right, 6 on either side.
Correct. So
Right,
on a
that means
5, you do
right.
it. So process capability on a 5 sigma is 5s on the bottom, or you wouldn't
No,
calculate it?
no. Bottom would always
Only on
be
a
6
6.
standard deviation.
Okay. Okay.
Right. So if your process working at a 6 sigma level, what that
Mhm.
means is your CP would be equal to 2. Why? Because remember, we said between lower and upper specification limit, you can fit 6 standard deviation on either side of the mean. If
Right.
mean is exactly at the center, that means from mean to upper 6 and from mean to lower 6, 6 plus 6 is 12 standard deviations.
Okay.
Right? So
Right.
12 standard deviation, that means, if you look it up in this formula,
Mhm.
the value for CP should be equal to 2. In other words, you can calculate Z short term is 3 multiplied by CP.
Okay.
So value of CP is 2, C 3 multiplied by 2 is going to be equal to 6. Right?
Sure.
Okay. But CP is a short-term measure of process capability. It is the could-be performance. It is not the actual performance of the process, right? Because it is not taking into account the process shift. It is saying USL, LSL, USL minus LSL. It is not taking into account where is the mean,
Mhm.
right?
Right.
So by design, what is the process capability? It is telling us. Okay. Now, to know to calculate, and there is limitation as well, and I'll show you the example why. So if you look at the process on the left hand side, upper specification is 140, lower is 220,
Mhm.
right? So if we see the formula, upper minus lower, 140 minus 20 is 120 divided by 6 standard deviation. Standard value for standard deviation is 10.
120
So
divided by
120,
6.
yeah, divided by 6 multiplied by 10 is 60. So 120 divided by 60 is 2. Value for CP is equal to 2. Z short term is 6 here, right? Because Z short term is CP multiplied by 3,
Right.
right? Now, but here it looks fine, right? So upper, lower, process exactly in the middle, mean exactly at the center. Let's look at the one on the right hand side. And let's calculate. So here upper specification limit is still 140.
Mhm.
Lower is still 20. 140 minus 20 is 120.
Mhm.
Standard deviation is still 10 because it is calculating standard deviation within the process.
Mhm.
So 6 multiplied by 10 is 60. CP is
Still
still
2.
equal to 2.
Mhm.
Do you think it is right?
No.
Because half of the process is outside the specification limit,
Right.
right? So with this process creating 50% of the defect almost, and we are saying Z short term is equal to 6, just because CP is equal to 2, it is not correct, right? So this
Right.
is a limitation with CP. It doesn't take into account where the mean is. Okay, and also if there would be a lot of times in the process when you would not have upper and lower both sided specification. right? So sometimes you might only have one-sided specification. What do you do in that case? Because the formula of CP is USL minus LSL,
Right.
right?
True.
So we have another measure called CPK. Okay, CPK is the it is the lower of CP with respect to upper specification limit and CP with respect to lower specification limit. I'll quickly show you. This is the formula: USL minus Y bar or X bar divided by 3 standard deviation with CPU, and CPL is Y bar or X bar minus LSL by 3 standard deviation. CPK is minimum of CPU or CPL. Okay, so since it is not covered in the curriculum, is the extra information that I'm trying to give you, just so that the concepts are clear, right? So I don't think there would be any questions in the exam from this, but still, as a green belt practitioner, you should know. Okay. So if we look at the same example now, if we calculate CPK here, in the left hand side, it'll be same. Oh, sorry, I navigated. Right. Yeah, on the left hand side, it'll be same, right? 140 minus 80, which is gonna be sorry, 140 minus 80 is gonna be 40 plus 20, 60 divided by 3 standard deviation, which is 30, which is gonna be 2, and 80 minus 20 is gonna be 60 again divided by 3 standard deviation, which is 3 multiplied by 10. It is again gonna be 2. So CPU is 2 and CPL is 2, right? So CPK is going to be equal to 2 in this case.
Right. Which,
right,
in a perfect scenario, should be.
Yeah, which is in a perfect scenario should be, absolutely, because it seems like a perfect scenario, mean is exactly in the middle. But if we look at it here, 140 minus the mean, and mean is again 140. It is 0.
Right.
Divided by 3 standard deviation, which is going to be 0. CPU is going to be 0 here. Now let's calculate CP with respect to L. So CPL is 140 minus 20, which is 120 divided by 3 standard deviation, which is 120 divided by 30.
So 4.
4, right? So CPK is 4. CPL is 4 and CPU is 0. What should be CPK?
0.
0, because CPK is minimum of CPU or CPL. Because this process is performing very well as compared to lower specification limit. But with respect to upper, it is all over the place. Right? So that's how you calculate CP, CPK, and Z score, and this is how you relate to. This is how you can compare the Z score and the CP value. Okay, we're good up till now. Shall I move ahead?
Yeah, I think I'm good.
Okay, perfect. So we will try to find one second. Whenever I'm training, I tend to have too many PPTs open. Okay, so we are at the original PPT. Introduction to Minitab. I'll not go to the slides. I'll directly show you Minitab. How does it look like? It's amazing software. It's a boon for the Six Sigma professionals. So, so I'm using an older version since it's a paid out version. I don't want to spend any more money on this. I'm using Minitab 16. So it's the current version that they have. I think it's Minitab 18 or 17 point something. So which is a lot better than this one. but I am able to survive with this, so not changing. So it looks just like Excel.
Mm-hmm.
Okay, the one in gray here, these are the headers, so you can update the data here. So the moment I update a text here, the moment I update any text here, you would notice this column C1 converted to C1T. T stands for text. So after that, even if I put in any values here, it will still be considered as text, and it will not allow me to run the analysis. This is a session window. So all my statistical results will come here in this window. Data, there's a data input screen. I can input the data in this.
Mm-hmm.
And these are the various things that I can do. Oh, there are loads and loads of it. You know, we would only be covering, I think, 5% of it in this particular session.
Right.
I would probably know about 40% of it. So 60% is still the unknown territory.
Yeah.
And statistics is always like that. You know, the more you explore, the more you find out, oh, there's a big ocean to
Right.
cover. So after a while, you give it up unless and until you want to do PhD in that. So uh, so there are a lot more stuff. We'll only touch upon, you know, what is relevant to us. And so this is Minitab. We don't want to know who developed it, the data window toolbar, etc. You would have the presentation, so you would see the slide. We'll not spend time here on this. You have Minitab tutorials as well. And then you have a good feature called Minitab Assistant. So if you click on graphical analysis, for example, it can tell you, you know, depending what is your objective. You want to plot the graph with distribution of data over time within variable, all that. So it's kind of a guide. You know, it will guide you through what you want to do. Okay.
Cool.
I will skip this. Come to histogram. Have you seen histogram and have you prepared histogram in the past?
I'm gonna go with no. Once we see it, I may.
Okay, it looks something like this.
Okay.
Okay.
Looks almost like a regular graph.
Yes, it is a regular graph itself, and for some reason somebody has made it in blood red color.
Okay.
So how it looks like, and how do you plot the histogram in? So let me just take this data. Okay.
Mm-hmm.
How easy? I'm just trying to show you how easy it is to plot a histogram here. So you have the data here. So what histogram would do? So I go to graph. I go to histogram. Simple histogram. Okay, select the row, and that's it. It plots a histogram for me. So it divides the data into bins, and every bin it will plot. You know, so we have this bin which has the maximum data point. So this bin value is from 27.5 to 32.5, and 4 data points within this value. Okay, so that's histogram. I will show you the other ones. Okay, I'm not going through this right now. I will. Okay. One second. Yeah, sorry. So like we have histogram, we have another, there's something called box plot. Okay, if I click here and do the cycle time, it will plot something like this. Have you seen this chart before?
I've never used one. I've seen one, but I've never used one.
Right. It's an amazing graph. So what it does is it breaks down the data into 4 quadrants, 25, 25, 25, 25% each. The middle line is the line for median. So if you bring your cursor here, it will give you the values. Q1, median, Q3, IQ, whiskers. Whiskers are these lines. And N is the total number of data points. So by the looks of it, you can see that, you know, this particular portion here. So we, after median, you know, there are a lot of data which is on the higher side.
Mm-hmm.
So apparently there is a box plot for cycle time. So we know that quartile 4, quartile. So what is quartile? So from this point to here is quartile 1, right? This to here is quartile 1. This is Q2. Q2 is the line for median. This is quartile 3. So quartile 1, quartile 2, quartile 3, and these are the whiskers. Any data point, if it is outside the range, it will show it as an outlier. I will show you. This is 30, I change it to 130. Okay, so I run the box plot again. You see this? It has shown this particular data point, which I converted to 130 as an outlier. Right? This is not the normal behavior of the process. Okay. Okay, now